Hello everyone, I'm Gaurav, PhD student at Georgia Tech Database Group, advised by Dr. Arulraj. Today I'll talk about EVA, a symbolic approach to accelerating exploratory video analytics using materialized views. To set up the stage for this talk, video data is ubiquitous and cheap. According to the Wall Street Journal, 770 million surveillance cameras are in use today. These cameras can capture video data, for example, at a traffic intersection. Similarly, autonomous vehicles are getting popular these days, and a single vehicle can generate 300 gigabytes of data per hour. On the other hand, we have a lot of real-world applications like traffic analysis, crop health analysis, anomaly detection, climate change, and so on. Luckily for us, because of the recent advancement in computer vision, algorithms can accurately perform on multitude of tasks. For example, according to the Bloomberg report, AI systems are even surpassing the humans in an object classification task in a controlled environment. However, traditional database system cannot handle visual data. So essentially, we have a lot of video data ready to be queried, and accurate computer vision algorithms capable of extracting rich information from the videos. Now, this opens the research opportunities for accelerating visual queries. To tackle these challenges, Georgia Tech Database Group is building EVA, an end-to-end video database system. This involves rethinking components of database system like video, query language, storage management, materialized views, distributed query processing, and query optimization. In this work, we'll focus on materialized views. To motivate the problem, let us consider a case study where an officer is looking for a suspicious vehicle in a surveillance video data. The witness provided the information that the suspicious vehicle was spotted in the evening and was an SUV. So such a query entails applying object detector on the video data with timestamp, let's say greater than 6 p.m. and filtering out the objects which are labeled as cars. Subsequently, it further selects the subset of those cars, which are SUVs. Now, this is just the beginning of the exploratory analysis. Based on the information from the previous query, the officer further narrows down the search space and starts searching for the license plates of the red SUVs. Once he gets hold of the license plate number, he tracks the suspicious vehicle for a longer timestamp to capture the vehicle trajectory. This is a typical example of a exploratory video analysis. So if we closely observe these queries, we find that there are multiple overlapping executions of UDFs like object detector, license plate, and so on. Given that these UDFs are typically wrappers around deep learning models and are therefore expensive to compute, reusing the results of these UDFs across queries is a very beneficial optimization. Now I formally define the problem statement. The goal is to accelerate exploratory video analysis by automatically materializing and reusing outcomes of expensive user-defined functions. There are three key challenges. One, identifying the reuse opportunities across multiple invocation of the same UDF. Second, how does the UDF reuse impact the query optimization decisions? Third, how to automatically rewrite the query to leverage the materialized views. Next, I'll hand over the slides to Andy, who will walk you through our approach and the results.
Hey, I'm Andy. Next, I will present the approach and the results. So here is a high-level overview of our approach. Symbolic predictive analysis. The goal of it is to identify the degree of reuse across the query. And we use techniques from programming language research to achieve this. The second component is materialization aware cost model. We exploit the fact that the I/O overhead is much less comparing to evaluating UDFs. We reorder UDF-based predicates using a new ranking function in EVA. The third component is logic reuse. In EVA, when the query does not specify the physical model, the system will pick up one, just like the object detector in the case study. Lastly, we do rule-based query plane transformation. For the sake of time, we will present the details of the three highlight techniques in the following of the talk. This is the system architecture diagram of the system. On the left, you will see a typical life cycle of a query goes through parser, query optimizer, and execution engine. Our system makes changes to the query optimizer, and we make 4 changes. The first one is identifying candidate UDFs, which are the ones worth materializing. The second step is to compute UDF signature so that we can uniquely identify the occurrence of the UDFs across the queries. We will talk about the third step, materialization-aware optimization, and fourth step, rule-based transformation, in later slides. We also add 2 new components, Symbolic engine, which powers the symbolic analysis in EVA, the UDF manager that stores the metadata for historic UDF executions. Moving on to this first component, symbolic predicate analysis. The first step is to extract the predicate associated with the UDFs. For example, the predicate associated with the object detector is timestamp later than 6 p.m. And similarly, the one associated with the vehicle model is timestamp later than 6 p.m. and label equal to car. The associated predicate defines a subset of tuples the database must evaluate the UDF on. The mappings between the predicate and the UDF is stored in the UDF manager. In symbolic predicate analysis, we define 3 key operations: the intersection, difference, and union. As the name suggests, the intersection predicate denotes the overlapping commutation between 2 UDF invocations with the same signature. The difference predicate denotes the non-overlapping commutation. And the union predicate denotes the commutation from either of the UDF invocations. The number of atomic predicates governs the capacity of the symbolic predicate analysis. So it is important to simplify the outcome of these operations. In EVA, we use computer algebra system to reduce predicates. Here, we give a high-level idea of the algorithm. First, we convert input predicate to disjunctive normal form. Secondly, we independently reduce every conjunctive within the DNF. Thirdly, we repeatedly pop 2 conjunctives and check whether it is possible to reduce their union predicate. We leave the details of the algorithm in the paper. Next, we move on to the materialization-aware cost model. So the question we try to answer here is, what is the optimal ordering of evaluating the UDF-based predicates? For example, in this query, we have vehicle model and color as UDFs in the predicates. In the traditional database systems, we have this ranking function, which depends on the selectivity of the predicates and per tuple predicate evaluation cost. So the idea here is we want to parallelize the evaluation of inexpensive and highly selectivity predicates. The key thing missing here is this ranking function does not consider available material results for UDFs. In EVA, we design our own ranking function. The intuition here is we modify the function to include the cost of the running UDF only on the tuples which are not in the materialized view. In order to identify the number of tuples not in the materialized view, we use the results from the symbolic analysis. We use the difference predicate to find roughly the selectivity of tuples that we need to compute. In EVA, we use this updated ranking function to reorder the predicates. Next, we move on to rule-based transformation. The first rule here is where we leverage the apply operator to transform the UDF expression in the selection operator into relational operators. UDF consumes input from the same relation, and we apply the predicate on outcomes of results. Once we have UDF extract out from the predicate into the apply operator, we can then leverage the second transformation. Here first, we do a left-out drawing with the materialized view according to the UDF to directly read the results. Secondly, we have a conditional apply operator to pass the tuples to the UDFs for which we don't have results. Thirdly, after executing the UDF, we append the results to the same materialized view and also update the entry in the UDF manager. Moving on to the evaluation, we try to answer the following 5 questions in the evaluation. In this talk, we'll present results for the first one. How does the UDF-centric reuse algorithm in EVA compare against reuse algorithms in traditional database systems? First, I'll briefly introduce the workload. This table shows example queries in our workload. We use patterns like zoom in, zoom out, and shifting to control the extent of reuse in our workload. Using these patterns, we construct 2 benchmarks. vBench low emulates a scenario where the analyst skims through different parts of the video. Therefore, the average overlap by 2 subsequent queries is low. In vBench high, the analyst iteratively refines the query over a particular part of the video as a law officer case study. In this case, the average overlap is 50%. We run our experiment on a server with 28 cores and 1 NVIDIA GPU. We compare EVA against 3 baselines: no reuse, hash stash, a technique used in traditional database systems; key value function caching, which is pretty simple as you cache results and then you reuse them at execution time. We show that EVA outperforms all the baselines on both workloads. Compared to hash stash, EVA is 1.2 times faster for vBench low and 2 times faster for vBench high. In the graph, we can also see we're better than function caching. This is because the function caching suffers from hashing overhead at runtime, and it misses on the materialization-aware optimizations such as predicate reordering. We would like to thank the organizations that are supporting our research. Thank you.